this time now, and I'm very pleased to introduce Robert McCann from University of Toronto. Robert is like one of the founders of optimal transportation theory, and he's going to talk about glimpse into the differential geometry and topology of optimal transport.
All right. Well, thank you very much. I'm very grateful to Yunhan and to PIMS for arranging my visit here. And it's always wonderful to be in Vancouver, especially when the sun is shining. So this is the first of 3 lectures that I'm giving here this week, and so I thought that I should try to give a kind of a survey and introduction with some new perspectives, but I'm going to apologize to the experts in advance for saying some things you've probably heard before. So I'm going to talk about optimal transportation today. On Wednesday, I'm going to talk about a new variant of the problem that I started to look into with the postdoc, and on Friday, I'm going to talk about some applications to economics, which are also quite new. But so, what do I have in mind when I think about optimal transportation? I have a distribution of mines over the surface of the countryside that are producing iron ore, maybe a total of 1,000 tons per day. I have a collection of factories distributed over the surface of the countryside, which are consuming the iron ore, maybe also a total of 1,000 tons per day. And I know some cost function, which tells me the cost per unit ton transported from a mine at X to a factory at Y. And I want to decide which mines should be paired with which factories in order to minimize the total transportation costs. Maybe I should have also said, so there's a preprint by the same title of my lecture on my website, or also on the archive. You're welcome to download. So you have all these mines and all these factories, and you're trying to pair them together so as to minimize total transportation costs. This problem has various applications. So another one that's pretty well known in economics is that if you have a group of men and a group of women, and it's sort of sometimes called the marriage problem, you want to pair the men with the women in such a way that nobody has, you can't find 2 people who are sufficiently unhappy with their partners or would be sufficiently happy with each other that they're willing to both leave their partners and join each other. And so this is, a variant of this is used on the medical school and residence match, where you're trying to pair up medical students with residency programs. And in that context, this cost, you change signs on this cost, and it would be a total surplus, a total value of pairing resident X with school Y. And you try to balance the value of to the resident and the value to the school in such a way that you can give everybody a partner that they're happy with. Happy enough with that you come out with a stable solution in the sense that nobody wants to leave their current partner to go to somebody else that's willing to take them. Of course, when you have finitely many factories and mines, this is kind of the prototypical linear program. It's the linear program that it was one of the original motivations for the development of linear programming in the 30s, 40s, and 20s even. But mostly I'm going to think about the case where I have so many factories and mines that I prefer to think of them as some kind of continuous distribution, maybe sitting on a line or in space or on some manifold, like the curved surface of the Earth, some kind of manifold with geometry. And so typically, I mean, you could think of this very abstractly and think about the setting for the mines and factories being complete separable metric spaces, but typically for me they're going to be manifolds, M plus and M minus. You can just think of Rn if you like. And the distribution of mines will be some non-negative measure on the first manifold, and the distribution of factories will be some non-negative measure on the second manifold. And if the total production equals total consumption, then I can set the total mass of this to be the total mass of that, and if it's finite, I can normalize it to B1. So now I'm dealing with probability measures, and I'm sort of interested in how the cost, which somehow reflects the geometry of these manifolds, influences or tells me what the most efficient way to pair particles on the left with particles on the right is. And so typically I'm going to think of this as being some kind of continuous cost on the product of the 2 manifolds. And sometimes I'll want a name for the product space, so let's call it N. And there are different senses in which you can think about pairing these 2 measures. So somehow the original idea of Monge was find a mapping G from the left space to the right space. And he was interested, he was interested in mappings G which push forward the first measure to the second measure. So in other words, for every set B over here, I look at the consumption taking place on that set, or the number of women in this set, and I ask that when I look at the pre-image of B over here, under G, that the total production, or the total number of men in this pre-image, should equal the total consumption, or the total number of women over here. So I'm going to write G pushes forward mu to nu if mu plus of G inverse B is equal to mu minus of D for every such D, say measurable D. And so 200 years ago, Monge was asking this question where the two measures were uniformly distributed over two sets of the same volume in R3, and the cost function was the Euclidean distance, and he asked how can you pair molecules of the set on the left with the set on the right in a measure-preserving way so as to minimize the Euclidean distance. So associated to this cost is, so I look at the cost of shipping from x to g of x, I weight that by the amount of stuff being produced at x, and I integrate over m cost. This would be Monge's cost. And he was interested in the minimization problem, compute the infimum of that overall measure-preserving maps G. G which push forward mu to nu. And okay, so it's well known that this is a little bit of an awkward formulation because this is a very nonlinear functional in G, and this constraint doesn't have nice compactness properties, so it's not even clear that a minimum exists. And you can think, for example, if this measure was concentrated in one point or finitely many points, and this one wasn't, there would be no map that does this. But on the other hand, for lots of nice measures, we now have a beautiful theory that tells us not only is there a map that does this maybe in the measurable class of maps, but if you put lots more structural assumptions on C and on the densities mu and nu, so sometimes I'll want mu and nu to have densities and coordinates, and I'll denote those densities by f plus and f minus. If you put extra structure on here and extra structure on the cost, then you can hope that this map will even be continuous or maybe differentiable, and then you can start to do analysis with it. So maybe a good example to keep in mind is that you take something like the inner product of x with y, or the distance between x, y squared. These are actually equivalent problems because the difference between this cost and that cost is x squared plus y squared. And when I integrate something like this, again, if I put cost equals x squared, I just get the second moments of mu plus. And if I put cost equals y squared, I just get the second moments of mu minus. So the only part that cares about the interaction between the two terms is this cross term here. So if I choose this cost here, then, and if mu plus is absolutely continuous in coordinates, then there's a very nice theorem of Grenier, which is pretty well known by now, that says the minimum is uniquely attained let me say optimal G and moreover G is uniquely characterized by the fact that it can be written as gradient of a convex function. And moreover, so this was on subdomains of Rn, or Rn, let's say. So in this case, so somehow let me give you some feeling for this. So what it means to be a gradient is that the map is sort of irrotational. And somehow if you're taking a thing here and you were rotating it when you put it down there, you would be increasing the distance squared. And so in order to keep the distance squared at minimum, you don't want to rotate things. And so this map should be derivative of something. And on the other hand, you also don't want to take something here and flip it over end when you're bringing it here, because that would also increase the distance squared. And so you would prefer to keep the orientation the same. And so the derivative of this map here, which would be the Hessian of U, wants to have all non-negative eigenvalues. If you have a negative eigenvalue here, it would correspond to flipping things over. So this kind of thing gives you some canonical way to reparameterize any measure mu minus by a given absolutely continuous measure mu plus. So you could take this to be uniform on the unit ball, or maybe a Gaussian, or uniform on the unit cube, as you prefer. And so there's some connection already to geometry with to geometric inequalities with this picture that's known for 15 years or so now. And let me just show you, because I can do it in a few minutes, and it's sort of a beautiful illustration of one of the kinds of applications that you get. So this story has applications to, I guess, proving inequalities, sharp constants, some new, some simplified proofs of old inequalities, finding solutions to nonlinear partial differential equations. So some things on the pure side, including nonlinear diffusion type equations, including very nonlinear elliptic equations like the Monge pair equation. And it also has very applied applications like, well, so for example, people have tried using this a little bit in image recognition. So you have a picture on the left and you want to pair it with a picture on the right. And you want to figure out which features on the left correspond to features on the right. And one way to do that is try to pair pixels on the left with pixels on the right so as to minimize average distance squared, where the density here would be something like a grayscale intensity. So people have tried using this for tumor excision, actually. So you have a very high resolution MRI image that was taken a few weeks ago, and now the surgeon is operating real time, and he's getting a crummy real-time ultrasound image, and everything's moved around because you've opened up the person's head. And you'd like to take the real-time ultrasound image and match it to a high-resolution MRI image and figure out where are the margins of the tumor that you can see very clearly over here. And so one thing that people played with for doing this is using different kinds of costs to try to ask what gives you the most faithful connection between the two pictures. All right. It has applications in weather forecasting too, and they're the stuff that's being paired are air masses moving around. So, I claimed that this thing here gives you some simplified approach to proving geometric inequalities, and somehow the grandfather of all geometric inequalities is the guy's parametric theorem. And so let me tell you a little bit how that works. So here I have two sets in Rn, and let's take the second one to be the unit ball, and let me take the first one to have the same total volume. And then the isoparametric theorem states that if these two guys have the same volume, then the perimeter of the first guy is longer than the perimeter of the second guy. And so somehow there's geometric information about the sets. And the idea of the role of optimal transportation in these kinds of problems is that having an optimal map between these two sets gives you a way to localize this sort of inequality. And so if I use Grenier's theorem, it tells me that whatever the shape of my M plus, I'm trying to pair it up with my M minus. Let me take the F plus and F minus to be uniform densities, so characteristic functions of these two sets. So I have a uniform mass here, I'm trying to pair it up with the uniform mass there. This is the unit ball. Grenier tells me that I can actually find a map that does this, and which is gradient of a convex function. And so let me see, what does this constraint mean? So the constraint is telling me that if I took this to be a very small ball, if I localize this thing, it's telling me that mu plus of a small ball around some point x naught is going to be equal to mu minus of a small ball or an ellipse, the image of this thing, so let's say g of dr of x naught. And this is approximately, as R goes to 0, if I normalize by the volume of the ball, this will go to something like f of x naught. And this will go to something like f minus of g of x naught times a Jacobian factor. So this is the sense in which my mapping here is solving a very nonlinear differential equation. In this application, both f plus and f minus have density 1, so these factors are both 1. And I know that the thing under the Jacobian is non-negative definite, so I can remove the absolute values, and I solve the Monge equation 1 equals determinant d2u for some convex function u, which depends on m plus. I can take the nth root of this fellow, and now I can apply, this is the geometric mean of the non-negative eigenvalues of u, so that's less than 1 over n times the trace of Hessian u. And the trace of Hessian u is better known as the Laplacian of u. So somehow I have this local domination of the geometric by the algebraic mean, arithmetic by the geometric mean. And I just want to integrate that over m plus. And on the left side, I get volume of m plus. And on the right side, I get something that's crying out for integration by parts to be turned into a boundary integral. And so this is 1 over n integral over boundary of m plus derivative of u dotted with outer unit normal with respect to surface measure. And the final ingredient somehow is that gradient of u is being mapped into the unit ball, and so gradient of u is never bigger than 1. So this is less than 1 over n perimeter of boundary of m plus. Now this is equal to volume of the unit ball by hypothesis. And in the case where m plus is actually equal to the unit ball, the mapping would be the identity map. I'd have the identity matrix under here, and all these inequalities would become equalities, and that would tell me this is 1 over n perimeter of the unit ball. And that's the conclusion I wanted, that my set has longer perimeter than the unit ball. So this is supposed to give you some indication of why it might be interesting to solve this kind of problem. And so now I want to spend the rest of the hour talking about understanding why should it be that this should be soluble, and how can I understand these kind of properties of the mapping G. And okay, so this kind of formulation went back to Monge 200 years ago. Big progress happened about 60 years ago, when Kantorovich suggested reformulating this as a linear program. So Kantorovich's idea was, instead of forcing every mine to supply x to supply a single factory g of x, let's allow each mine to distribute its production over a family of factories. So instead of looking for a mapping G that rearranges u plus to give me u minus, let's look for a non-negative measure, gamma, on the product space. And it should have the property that when I, so here is my product space, with the measure mu plus on the horizontal and the measure mu minus on the vertical. Now I'm looking for a distribution of unit mass over the product, such that when I project down here, I see this guy, and when I project over there, I get this distribution. So if I define the horizontal and vertical projections to be pi plus of xy is x, and pi minus of xy is y, what I'm asking for is the image of gamma under the vertical projection to be equal to mu plus. And similarly, the image of gamma under the horizontal projection should be equal to mu minus. And so Kantorovich suggested focusing on joint measures gamma in this space here. To each such joint measure, you can associate a cost. Cost of gamma would be the integral over the product of the cost of shipping from x to y, weighted by the amount of stuff that's going to be shipped from x to y. And Kantorovich's problem of 1942 was to minimize this cost over this set here. And this is a much better formulation because at least the cost depends linearly on gamma. The set of measures gamma that satisfy these constraints forms a convex subset. These are affine constraints. And it actually lives in, I mean, you can think of measures, according to Rees-Markov theorem, measures arise as the dual linear functionals on continuous functions. So I could think of this as living in the dual Banach space to this guy. Maybe put the suit norm on here. At least when these spaces are compact, and you need to fuss a little when they're non-compact. But this thing is even weak star compact in this dual Banach space, and then the Banach-Aloglu theorem tells you this min should be attained as long as the set is non-empty. And the set is non-empty because a candidate measure is product measure, mu cross mu minus. But it turns out that, I mean, this measure here is, the mass is spread all over this thing. At least if the mass of mu plus and mu minus are spread over their respective spaces. So it's very different from this picture here, where all of the mass was concentrated on a very thin set, a mapping G that took an x down here to a y up there. So this is the map y equals G of x. So this min is always attained, this inf may or not be attained. And the main approach to solving this problem is to show that this minimum is attained, and in fact, you take the minimizing object and you try to study it using standard techniques from the calculus of variations and show that something like the optimizer gamma has the property that it's support, which is the smallest closed set of full mass. Is not the whole square like it was over the whole product like it was for this guy, but is concentrated on a very thin set, so at least is contained at least gamma almost everywhere in the graph of some function G. And in cases where Monge's problem can be solved, this is usually how you go about solving it. You first begin with a minimizing gamma, and then you study it, and you try to show that there's some mapping G whose graph contains gamma almost all of its support. So I want to start out with sort of a more basic question, which is I want to try to understand why is it that when I study this sort of minimization problem here, I expect the mass of gamma to concentrate on a very thin set in this product. And I want to start by estimating the dimension in the product space of the support of gamma. And then we will eventually come to conditions that tell us, once we understand its dimension, we'll eventually come to think about when can it be written as graph of the map and when can it not be written as graph of the map. Maybe I should pause and ask if there are questions. And so the other, one of the take-home messages from this talk is that all the answers to all of these kinds of questions are, you don't have a lot of structure here to work with. And the answer to all of these questions turned out to be contained in somehow the geometry and the topology of this cost function and the two manifolds that it lives on. The answers also depend weakly on the measures, but not so much. So let's see. So let me first set, I want to define a function delta on n squared. N was the product space. And delta would be following function, c of x naught y plus c of x y naught minus c of x y minus c of x naught y naught. And there's a basic fact that goes almost, in the special case of distance on Euclidean 3 space, it goes back to Monge. And the basic fact is that this function here, which, of course, because of all the symmetries, it takes both signs on n squared. But the fact is that gamma is non-negative on support or sort of delta is non-negative on support of gamma. And let me try to argue why this should be true. So I take my support of gamma, whatever it looks like, whatever crazy set it is, and I pick a pair of points out of it, x, y, and x naught, y naught. And I claim that if I plug this point and that point into the function delta over there, what I get should be non-negative. And the idea is that gamma is supposed to minimize this cost. And so if this function delta is not non-negative, if it were strictly negative, do I have my, yeah, okay. So this function is positive when the cost of shipping from x to y plus the cost of shipping from x naught to y naught is less than the cost of shipping from x naught to y plus the cost of shipping from x to y naught. And if this inequality went the wrong way, which is to say if I had this, then this picture wouldn't be so optimal anymore, because hopefully I could take a little bit of the mass that's being shipped from x to y and send it instead from x to y naught. So I would add a little bit of mass here. Similarly, I would take a little bit of the mass that's being shipped from x naught to y and add it here. And then hopefully I could subtract it from these points in such a way that I don't affect the marginal projections. And if I can do that, then I've lowered this cost. And so then I wouldn't be a minimizer. And so it turns out that you can, in fact, do this addition and subtraction without affecting the marginal projections, and that's how this fact is proved. And I claim that this fact essentially tells us the dimension of the support of gamma, at least locally, near any point x naught, y naught, in the support of gamma. So this is a theorem of Brendan-Pass. The initial versions of it, the versions where the dimensions of these two spaces were the same, were a joint work of Pass and Michael Warren and myself. This is a theorem of Brendan's thesis last year. So if I fix some and what do I want to notice and set so I want to fix the last two arguments of this function and think of it as a function of the first two variables and observe if I plug x naught, y naught into this function, I get 0 because of the symmetries, because of these minus signs. And also, if I differentiate with respect to either of the variables, and at this point here, because of this minus sign, the derivative with respect to x of this term here will cancel that one. Or if I computed a derivative with respect to y, this term here would cancel that one because of the minus sign. And so x naught, y naught is also a critical point. And so that means that even if I'm not working in Euclidean space, if I'm working on some general manifolds with no geometry, I can still make good sense of a second derivative of this function delta naught y, at least at this point here. So maybe I should say Hessian is well defined at x naught, y naught. And the claim is also myself, Pass, and Warren. And the claim is that if gamma is optimal, then for any x naught, y naught in the product space, small radius such that when I intersect the supportive gamma with a ball of that small radius, that this intersection is actually contained in a Lipschitz manifold and that I can estimate the dimension of this manifold. And the dimension is n plus n minus half of the rank of H at x. So this is rank of H at x naught y naught. And so, for example, okay, well, yeah, so I need to tell you a lot more about this theorem, but for example, in the example we just looked at, and the dimension n plus and minus are the same, and it turns out the rank of H is 2n, and so then this formula tells me it's an n-dimensional submanifold of a 2n-dimensional product space. And so that's already suggesting something like the graph of a map. And it's already telling me quite a lot of regularity information about that map because it's a Lipschitz submanifold, so it's actually, that graph is actually has a well-defined n-dimensional tangent space at n almost every point. Hausdorff n almost every point of this graph. So not only is this, do I expect this thing to have an n-dimensional space in this 2n-dimensional product space, I expect a well-defined tangent almost everywhere. So let me try to motivate this theorem a little bit and at least tell you the algebra behind it. Why should the rank of H come into the story? And somehow it's all this fact, this non-negativity. So let's so here's the heuristic, the counting argument, if you like. Fix x naught, y naught in support of gamma, then delta xy, delta naught xy is non-negative on support of gamma. So let's Taylor expand this function around this point. So at x naught plus delta x, y naught plus delta y, you know the first term, the zeroth term in the Taylor expansion vanishes, and so does the first term. And so what I get is the second term, which looks something like this. And then I get lower order terms. And this actually has a little bit more structure because, again, because of this minus sign here, when I take say a second derivative with respect to y, and then I set y equals y naught, these terms will cancel. Or when I take a second derivative with respect to x and set x equals x naught, these terms will cancel. And so actually the only thing that survives in this Taylor expansion are the cross terms. Mixed second derivative of c that come from here, so I guess there's actually a minus sign. Minus. Mixed second derivative with respect to xi yj, delta xi, delta yj. Plus lower order terms. And I should have said a hypothesis in this theorem is that C is C2, or at least locally near x naught, y naught, so that I can do this Taylor expansion. So what I see from this is that I can kind of control, if I think about diagonalizing this matrix H, and checking how many, it's a symmetric matrix, so it has real, all its eigenvalues are real, and I want to count how many are positive and how many are negative and how many are 0. And so, so H has 2n real eigenvalues. If delta x, delta y is an eigenvector corresponding to a positive eigenvalue, then this quantity will be, I guess, negative. But if I flip a sign on the last n components, then I'll get a negative eigenvector. Because I flipped the sign on these guys and not that fellow. And so, so the signature, the plus 0 minus signature of H, however many positive eigenvalues it is, I have the same number of negative eigenvalues, and so the number of 0 eigenvalues is the total dimension minus 2k. And k is at most, k is something between 0 and I think the minimum of n plus and n minus. Otherwise, this would become a negative number. And so this is sort of the maximal case where I have n positive eigenvectors and n negative eigenvectors, and then I get the strongest restriction on the dimension of this thing in that case. If this cost had some 0 eigenvectors, I wouldn't be subtracting quite as much, and I'd still have a dimensional bound on the size of the support, but it wouldn't be as tight. And if you think of another really extreme opposite example, take the cost to be constant or maybe 0, then the rank is nothing and I can have support everywhere. So for the 0 cost, all measures are optimal, including the product measure. Somehow this interpolates between, this tells me the algebra interpolating between these two things. But somehow this heuristic allows me to estimate the dimension. It doesn't really tell me how to prove the theorem, but maybe I should comment on somehow the strength of the theorem. So note, no assumptions on mu plus and mu minus. So even, for example, in one dimension, I take a measure that it has some singular parts, it has some gaps in its support, it has some non-singular parts, that could be my mu plus. I take another measure that has some singular parts, some zeros, some gaps in its support, that could be my mu minus. I want to pair these guys together. So R cross R. What's going to happen, so somehow the picture I've drawn is like this. So some of the singular stuff will get mapped into here. Then some of this absolute continuous stuff will get mapped into there. The middle part of this absolute continuous stuff might get mapped to this Dirac measure here. The right-hand part of this absolute continuous stuff might get mapped up here. And then the rest of this gets mapped to the last bit of that. So I might have a picture like this. This could be the support of my optimal thing. So maybe I should tell you another fact. So if, so example, if the mixed partials of C in one dimension are negative, then when I try to correlate this thing, that would be in this case here. It turns out that the best thing to do is to pair the leftmost mine with the leftmost factory and the next mine to the left with the next factory and so on. So I get a picture like this. That implies support gamma is non-decreasing in R2. If I flip the sign here, it would be non-increasing. And so the idea behind the proof of this theorem is that such a thing is still contained in a one-dimensional Lipschitz graph, because the worst that a non-decreasing set can do is be vertical or horizontal. Sorry, I'm sure green doesn't show up. vertical or horizontal, I can cover this whole thing with a non-decreasing function. And if I viewed it not in coordinates x and y, but rather in coordinates u and v, which are like x plus y over root 2 and y minus x over root 2, then what I would see is that the slope of v as a function of u can be at most plus 1 and at least minus 1. And so that's my Lipschitz bound. And it turns out that for this cost here, exactly this trick of looking at these new coordinates works in Rn. And for other costs, you sort of have to do, you can do an affine change of variables in y that makes the matrix of second partials be close to minus the identity matrix plus lower order terms which don't affect the outcome. Okay, so much for the dimension of the optimal thing. Let me turn to this question of when can I, of course, just being one-dimensional doesn't necessarily, if the sign changed, so if it was maybe positive in here but negative in the corners, there's nothing that tells me I might not have some stuff up there in this part of my optimizer. This is a local result. This could be one-dimensional decreasing. This could be one-dimensional increasing. If I have that, it's not a map neither as y over x nor of x over y. So next question is, is split gamma contained in graph G, gamma almost everywhere for some G, and there's an answer due to Gavin, Levin, and Gangbo separately, building on work with many other people, which says, which can be phrased in the following form. So if mu is absolutely continuous, first one, and for every x naught in M plus and y different from y naught in M minus, the mapping x in M plus to delta naught xy has no critical points. Save x equals x naught, which again, because of the symmetries, that function up there has to be a critical point. Then this is true. So let me rephrase this. When is that true? And yes. So somehow the critical point structure of the function delta or the function delta naught is enough to guarantee that the supportive gamma is contained in the graphical map. For this example here, it turns out that what we're asking to have critical points or to not have critical points is something like x minus x naught inner product y minus y naught. And if this is a non-zero vector, then this has no critical points at all. I guess no critical points. I should have not said anything about that. Okay. So this is a beautiful criterion. There are lots of examples which satisfy it. There are a number which don't. So let me tell you some of each. So for example, if I take cxy to be h of x minus y on Rn again, with h strictly convex or strictly concave, call this hypothesis A1 plus maybe. So that satisfies A1 plus. I call it A1 plus because there's a kind of symmetrical hypothesis where the rho of x and y interchanged. An example which doesn't satisfy it, take something like 1/2 x minus y squared restricted to the boundary of the unit sphere in Rn plus 1. So this is a very nice smooth cost. It's C2, but it doesn't satisfy this guy. And in fact, any time that both of these manifolds are compact, this is a smooth function, it has to have a maximum and a minimum, and then you're out of luck. In fact, no smooth cost on compact plus net minus can satisfy one. And it turns out that you won't generally have mappings in a case like this. A question you can still ask is whether the Kantorovich minimizer is unique or not. And it turns out that A1 plus implies uniqueness. Always assuming absolute continuity of one of the two measures. But of course, A1 plus won't apply if we're trying to do transportation on the surface of the round sphere with respect to a smooth cost. So I have a result with Pierre-André Chiappori and Lars Nestheim from a few years ago. Let's call it B1 plus. And where we actually allow this function to have critical points. It's the same hypothesis. But we allow only two critical points, a global min and a global max. So this thing implies uniqueness. It doesn't imply that you have this condition here. It works beautifully on examples like this one here. It doesn't work when the topology of M plus is more complicated than the topology of the sphere. So for example, you take M plus to be the 2 torus and M minus to be the 2 torus. You take a smooth cost on the 2-dimensional torus cross itself. Nobody knows the criterion that guarantees uniqueness of the solution. But we know that, I mean, the intuition is that for a generic cost, the solution should be unique, but nobody knows an example of a cost for which the solution is unique for all less than continuous measures. So maybe I record that as an open problem. Give a cost C, which is smooth, on, say, T2 cross T2, for which Kantorovich minimizers are always unique. Again, B plus is absolutely continuous with respect to coordinates. And somehow there's this, I could tell you a tiny bit more about Although it's not true that supportive gamma is the graph of the map in this case, supportive gamma does look like approximately like this, like a union of a map and something else. And so somehow, what seems like it's going on is that the Morse theory of this function, the number of critical points of this function, is telling you how many branches the optimal map has. But again, nobody has any way to make that intuition precise in a topology more complicated than the sphere. So everything is open over to us. I have a few minutes left. I guess what I would like to talk about in the last few minutes is if I'm in this case, A1 plus, and so that I know that supportive gamma is contained in the graph of a map G, when can I include more information about the map G? When can I rule out these kind of junk discontinuities here and to know that G is really continuous and maybe smoother? And I can mention for the distance squared cost that Caffarelli in the early 90s and Delanoë in 2 dimensions in 1991 and Kurbas in 1997 were able to give sufficient conditions for the smoothness of G when G was gradient a convex function U, solving a Monge pair equation. And so basically, now I need some control on the geometry of M minus. So if my M minus is like this, a union of 2 disks or something, I'm out of luck. There has to be a tear somewhere on the left, where the left stuff goes to here and the right stuff goes to there, and that will be a discontinuity in the map G. And in fact, for this particular case, it's an unpublished result that this tear is differentiable with a polar continuous gradient. But the results that are well known is that if you make this sky convex, then for the cost 1/2 distance squared, this mapping will be at least continuous on the interior. So if F plus and F minus are bounded above and below on M plus and M minus, then G is actually Holder continuous with some exponent alpha. And if, in addition, F plus and F minus are smooth, then G is smooth on the interior. And if you want smoothness up to the boundary, then you actually need up to, for global, you need also M plus convex and the boundaries of the 2 guys smooth. And in recent years, these kind of results have been generalized to some other costs. And the first work in that direction was by Ma, Trudinger, and Wang, who gave sufficient conditions for a result like this one here. And they eventually relaxed them to get a result like this one here. And Figali, Kim, and myself were able to show a result like this one here under the rougher hypothesis for these general costs. But what I want to do today is kind of paraphrase the conditions of Ma, Trudinger, and Wang that gave these positive results in the language, in sort of the intrinsic geometry of the costs. So it turns out that those are also related to this condition delta, this function delta that we introduced. So MPW, Ma, Trudinger, and Wang's O5 conditions sufficient for a smoothness of G can be rewritten as follows, or are equivalent to well, I guess they want M plus and M minus to be compact domains, bounded domains in Rn, and the cost to be 4 times continuously differentiable. And they want that for every x naught, y naught closure. So the only critical point of delta naught should be x naught, y naught. So that's quite closely related to A1. It's the symmetrized version of A1. They want rank of H to be full. And then they want two more conditions, 3 and A4. So A4 is the analog of these kind of convexity hypotheses. But to talk about A3 and A4, I look at this, H is a signature n metric tensor on the product space. So I can think of this as being like a Riemannian metric, except that it's not positive definite. It has as many time-like as space-like directions. Nevertheless, I can do all the same things that I would do in Riemannian geometry. I can define geodesics by the associated geodesic equation. I can define curvatures using the associated Riemann tensor. Use geodesics and curvatures on N. And so the analog of these two convexity hypotheses here, A4 asks that x naught cross m minus and m plus cross y naught are geodesically convex in the sense of this metric tensor H. So, in other words, if I take a vertical fiber over x naught, any 2 points here can be joined by an H geodesic, and it doesn't leave that vertical fiber. Similarly, any 2 points on a horizontal fiber over y naught can be joined by an H geodesic, which doesn't leave that horizontal fiber. And finally, at every x naught, y naught, if I look at a vector parallel to this horizontal vector, so a vector p of the form, I don't know, let's say p comma 0 or little p plus 0, where both of these are n-dimensional, and q of the form 0 comma q, where both of these are n-dimensional, so a purely vertical vector, the associated sectional curvature, Riemann curvature tensor, the associated Riemann tensor R of PQ, PQ should be non-negative. So this is kind of saying the sectional curvature of every two-plane like this in this n-dimensional product space should be non-negative if H, if P is orthogonal to Q, and P is P plus 0, Q is 0 plus Q. And I'm out of time, but so these 4 conditions plus a strong version of either A3 or A4 give you these kinds of positive smoothness results. Strong in the sense that you either want this inequality to be strict, or you want the convexity to be strict in the sense that the curvatures of the boundary are strictly positive. And A3 is sort of always necessary and sufficient for smoothness in the sense that if you have the wrong sign here for any pair of vectors that are horizontal and vertical, then you can construct a smooth, positive, bounded pair of densities f plus and f minus such that you get a discontinuity in the optimal map. So A3 is necessary as well as sufficient. And there are many beautiful examples now of costs that satisfy these hypotheses and costs that violate them. So for example, distance squared, Riemannian distance squared on the round sphere satisfies all of these things. Riemannian distance squared on a hyperbolic space or on a saddle in the mountains. So any negatively curved thing violates A3. Example where maps have discontinuities in that case. So maybe this is a good place to stop. Thank you very much.